Okay, let's take a look and see if we can get a quick review on some of the problems here. And this is the very first question. It should not have been a surprise. It comes right out of the GeoTol Pro workbook. It's one of the problems you've already done. But using the drawing below, calculate the virtual size for the identified features. Remember, when calculating virtual with MMC, holes appear smaller and pins appear larger. So on this very first one, what do we have to do? You know, look at it and say, well, I have to get the virtual size, the A, B, and C, be for this guy here. We look at it and they say, what is this feature? Oh, it's a hole. We take a look here. Okay, it's a hole. So how do you do maximum material condition for a hole? So if we take a look at the maximum material condition for a hole, it's the smallest hole. So we'll take our 190 at maximum material condition. So what is our position tolerance then at maximum material condition? We got 12 thousandths. Okay, now it says that holes appear smaller. So do we subtract or add that tolerance then? The hole's going to get smaller. So if we take our 190 minus the 12, we're going to come out with an 8 here, 7 here, and a 178. The answer is 178. If we come down to the next question, virtual size to A, and again, what do we have to do? We have to go and say, what is the maximum material condition of that feature? It's going to be 190 because it's a hole, smallest hole. Okay, and what is the position or perpendicularity tolerance at maximum material condition? It's 5 thousandths. Okay, we'll take the 190 minus 5, and we're going to come up with 185. Okay, if we go to the next one, we take a look at, okay, this time we have a pin. Okay, and we have 385 plus or minus 2. So what is the maximum material condition of that pin? 385 plus 2 or minus 2? Well, pins are going to get bigger, so we're going to take our 385 plus 2. Our maximum material condition is going to be 387. Okay. Now it's asking virtual size to A, B, and C. We'll take our position tolerance at maximum material condition is 10 thousandths. Now, do we add this or subtract it? Well, pins get bigger, holes get smaller. So if it gets bigger, we're going to have a 7 here, a 9 here, and a 397 is our answer. Okay. Again, we look at our perpendicularity tolerance. We want to find out, okay, what's our maximum material condition? For a pin, it's going to be 387. It's 385 plus 2 because the pins get bigger. It's maximum material condition, and then we want to know the perpendicularity tolerance at maximum material condition was 2, and we come up with 389. And we'll check it. Yep. So I think we got those answers there. Okay, let's take a look at this problem and see what the question is asking. It says use the drawing below right to calculate the smallest virtual or mating hole size possible for the ring. And it says pay attention to how the rings mount on the assemblies. Again, this is a problem you already had in the GeoTol Pro workbook. Everybody should have aced it. So if we take a look and say this area here deals with the hole. So we don't even have to look at that. Then we come down here and say, well, are we worried about position on this hole or just how it lays flat to the surface? So really that pin can move all over. It's just that we have to make sure that that ring can fit over top of that pin. So we're not going to look at the position right now. Cross that out. Okay. But what was the virtual size at maximum material condition of the pin? So we would have taken a 385 plus 2. That would have given us a 387 for the maximum material condition. And then we would have added 2 thousandths for the perpendicularity requirement. So we already really calculated that requirement. It's 389. So it's 389. Okay, this is going to be similar to the last one, except now it says use the drawing below right, that's this guy right here, to calculate the smallest or virtual mating hole size possible for ring number 2, and that's this guy here. But now that they're saying that that pin now is required to be positioned on there, and so anyway. What we have is an area, we're not going to look at this again because that's the hole. And what we're going to be looking here now is this guy here. We got the position. Okay, and again, you'd have to know the maximum material condition is the biggest pin. And so we got a 387. But we got actually, it's calculator again. You add the 10 to it, you get the 397. So what we have is a 397. Would be the virtual mating size, because the virtual size of the pin is 397 at maximum material condition. We just need a hole big enough to get over top of that, so it'd be 397. Okay, on this drawing we have a requirement that the ring just has to fit over the pin. It doesn't have to lay flat. We're not worried about any kind of position. So how do we calculate this thing? Well, we have to go and take a look at the drawing. And again, we're not going to look at the hole. I mean, we don't need the hole. All we need is the pin. And it just has to fit over that pin. And we're not going to worry whether it's perpendicular. We don't care about the position. All we care about is the maximum material condition of the pin. So if we say 385 plus 2, we'll say it's going to be 387. Okay, on this problem, I probably wind up getting it wrong just because I go too quick and put the wrong, don't complete the answer. But one of the things we have to do is use the virtual sizes previously calculated and the size tolerance below to calculate the perpendicular tolerance for ring number 1. So we got ring number 1 over here. Okay, so it says virtual size is calculated. So are we going to use this virtual size for this hole? No, because it's going to go over the pin. So let's not even look at this hole. And what we're doing is we're looking at perpendicularity. So we're not going to look at this position right here for now. We're going to look at the previously calculated perpendicularity at maximum material condition. It's 389. So that's a number we need. Now for the hole, what's the maximum material condition of the hole? It's usually the smallest hole, largest pin. So we got the smallest hole is 392. So let's put that up here, 392. Let's find out what the difference is between our maximum material condition of the hole, where it has to fit over the pin when it has a perpendicularity requirement of 2 thousandths. Okay, so we'll say 12 minus 9 is 3, 9 minus 9 is 0, 3 minus 3 is 0, 3 thousandths. And this is where I would have messed up. I would have just put in 3 thousandths and forgot my requirement. Is it ML or RFS? And we've already said it's going to be at maximum material condition. So 3 thousandths M. Okay, on this problem, it's really the start of a problem where we're just going to do one part of it. And it was to fill in the feature control frame for ring number 2. And we've seen this a number of times, this ring. And we've seen the ring that just has to fit over the pin. But in this particular instance, we have a feature, if I can get my, there we go. We have a feature here with the datums B and C that are going to then position over top of the part here. So what would we pick for that? We're going to pick perpendicularity, or are we going to pick position? These are the two that we've been looking at all along. So the answer is going to be position. That's that we put in there. So we'd put position in there, and that would be our answer. Okay, again, we have to take a look at using the virtual sizes from the previous exercises, and then to calculate the size tolerance for this feature right here. Let's go ahead and take a look and see what we have so far. We already said it was going to be position. We said, we got this datum B and C are going to locate us over here. Okay, and then we know we're not going to use this hole up here, so let's get rid of that. We're using position, so we're not going to use this perpendicularity. So let's go and take a look and see what we got. If we take it the maximum material condition of the hole, so it'll be the smallest hole, will be 0.403. Maximum material condition. Okay, and then what we're going to do is say the virtual size when it's located in position was 397. Okay, 13 minus 7 is 6. 9 minus 9 is 0. 3 minus 3 is 0. Okay, what we wind up with coming up with is 6. And again, I would mess this up because I would probably just write in the 6 being too quick, but we still have to get the M in there. So it's going to be position, tolerance of zone, the shape is diameter. We're going to go ahead and have a 6 thousandths maximum material condition, A, B, and C. Okay, on this one is another one that comes right out of the book, but it's an important one to remember how to do. So what I would probably do is pick the ones you know first. Because I know this is a datum feature symbol, so I got a symbol there. Okay, the surface of the part, that's the the datum feature. Let's see, with theoretical perfect plane, or it's the datum. So we got that guy there. Let's see, surface plate, or this is going to go ahead and be the datum feature simulator. And then the plane derived from the surface of the plate is simulated datum. Let's see what we get. Okay. So anyway, we got datum feature symbol, datum feature, simulator datum. Okay, the lid in the can type of feature with the bold pattern, the clearance holes, should start to look familiar to you now. And, if they say, what's the first thing we have to do when we take a look at a drawing? You have to grab and set up the datum reference system. And you say, well, what's the best features on here? If we take a look at these features here with the lid surface and the surface of the can, they're going to be tightly mating surfaces. That are really going to set things up for us if we go ahead and we say, okay, we're going to make that datum A. Okay, and the same thing over here. I think we could put our datum D right there. And we really want that line. Excuse me. Let's reset that. Let's go ahead and make datum A here. And your datum D is really So that's going to get us set up. We have 6 degrees of freedom, and that's going to help us constrain 3 degrees. We'll have one translation, and then we got a couple rotations that are going to be taken care of by setting that up. Then the next thing is, well, what would be the secondary datum be? And we could take a look. Well, is it going to be the the whole pattern? Is it going to be this outside diameter? Is it going to be the pilot hole and the pilot? And I'm going to say why we're going to pick the pilot and the pilot hole. And the reason is, if we take a look at how that's going to set things up to constrain 2 more areas of how this part will be set up when it goes in. So anyway, if we take a look at some of these tolerances at the maximum material condition, we got 2,000, we got 6,000s here. If we take a look at the maximum material condition here, we get 8,000. We got like a 2,000s clearance there. And that's at maximum material condition because we're at 0 at maximum material condition. But if we take a look at the holes, we got the 12,000s there. If we take a look at the maximum 279, or if we're at 250, we got pretty much slop if we got a 1/4 inch bolt, and then we got a 279 clearance hole. So that thing's going to slop around in there quite a bit. This thing's really going to tighten us in there, constraining 2 more translations, so that it's really going to fit in there nice. Now we got this third datum, and do we really need that? If this lid is going to pop in there, do we really need to constrain a rotation on that? And like I said, well, yeah, you probably could put another one on there, but it's really not needed, because that lid can spin on this can, and it doesn't really matter where it is on that can. So right now we're going to have only pick datum A and datum B, and then E and D for this problem. Okay, let's take a look at this one, because it was I gave people more credit on some of these because it was a poorly designed question and there was more than one answer. But this is starting to look familiar. On the previous question, we put the datums on. Now we have to say why. I picked my primary datum, and I think most folks got this as they're seeing it as the flat surfaces. And now we have to say why. Why did we pick those surfaces? It sets the orientation of the parts when the screws are tightened. Okay, on this one, again, I think most people are getting that that we're going to pick the pilot hole and the pilot as the secondary datum. But then, the reason why did we pick this thing? And there actually was 3 answers to this. The only one that didn't work was this provide flats, but it aligns the parts for the screws, provides good round features that will center the screw holes, sets the orientation. All those would have worked. For now, we're going to put this one in here and hit submit. So I gave you credit, even if this one came up wrong. I gave you credit for the question, as long as you got this part right and you picked one of the 3 that were good. Okay, and then this tertiary datum. So did we pick anything? I think most people got this thing right, that there's not going to be any tertiary datum, because this, the lid can really sit on top of the can and spin around. It's not needed. Okay, this is one of the questions I had a grade manually, but what's happening here now? The designer placed the datum feature K in this location, and then they picked the datum feature R in this location. And what's the difference between R and K? And if we take a look at R, it is in line with the dimension line. This establishes the center plane. And then the datum feature K here was away from the dimension line. Establish a plane from the high points on this surface. Okay, let's take a look at this problem, because these can be tricky if you're not organized. Let's take a look. But it's so important to understand how the datum reference system works and how it constrains degrees of freedom. So what we're looking at is this feature control frame. We have a primary datum E, secondary datum F, and a tertiary datum B. So let's go first take a look at the primary datum E. So where is it? Okay, it's right there. Okay, and what does primary datum E mean? I mean, it's lined right up with that dimension line. Let's go ahead and actually draw something in and say, well, okay, we got one there. I didn't like where that was. Let's put it up where it belongs. Okay, so if we look at the primary datum E is really the two planes that give you centerline planes of that circular feature. So what degrees of freedom would that constrain? So if I took a look in this direction, okay, that's your y direction. I'd say, yep, that will constrain the y direction. If we look at this direction, yeah, that's our x direction. Yeah, that'll take care of that. Now z, it can still run back and forth on that two centerline planes. So no, z is not going to help in this case. Now, can I rock or rotate back and forth this way? That would be back and forth this way. So that would be the u. I say, yep, that would constrain u. And then can it rotate back and forth if this plane's here? That would be our v. I'd say no. But w, that wouldn't help either, because it can rotate on that axis. So the two that aren't going to be constrained are the w and the z. So the rest are there. So it's going to be x, y, u, v. So we just put in there the primary is x, y, u, v. Okay, and again, it can be tricky. Okay, let's get back into this again, and we're going to move on to the next secondary datum to see what that's going to do for us. So let's see if we can erase some of this stuff here, and we'll get rid of that, and we'll get rid of this. And we only had 2 degrees of freedom left over that we could possibly have. So our next datum was F. Where the heck is F? What does that do for us? We had E, H, D. Oh, there's F right there. Okay, what is F doing for us? Boy, that seems like a nice plane that's going to go right there. So what is F going to do for us? Well, if we take a look at F, that's going to stop us from moving along the z-axis, but it doesn't really help us in terms of rotation on the w, because it could still spin. All it's going to do is stop us there, but the part can still spin. So I'm going to say no to the w and yes on the z. So we got z. So now there's only one left. Let's go ahead and take another look then. I'm going to get rid of this and this. Let's see. Let's get rid of this. And now we're going to look at B. What's going on with B? And look at that. B is right next to here. And then we got this nice feature here that's going to, let's see if we can just draw a plane down there. We got a feature there. And what's going to be left is really the only thing is W is left. And yeah, that will keep us from rotating back and forth. So we'll put W in there. Okay, so X, Y, U, V, Z, and W. what I'm finding out on these tests, it's really hard to do design good test questions. And as I go through and do the review, I was like, boy, these poor guys that had to do this question, I would have just froze up if I had gotten it. But some of the things I think that would have helped out is if I had said, okay, this is number one, part one, and then this is part two, and this is over here actual condition, and we just go ahead and mark these things so we know what they are. So we got part one, part two, and what the actual condition is. And so let's take a look at part one and say, what does part one mean? And what we're going to do is we'll take a look at this feature control frame. And what happened is in the feature control frame, they said that A is the primary and B would be secondary. Okay, so what's going to happen now, we're going to have this A here, and then our B, which would be the secondary datum, here. So what's going to happen if that's the primary datum is that that part's going to lay nice and flat on that primary datum. Now in the second part, number two, the primary datum was B, which was the centerline plane. Let's get rid of that and give you a little better thing. And it's in line with that dimension line too. So that's important to know. So that what it's going to do is with the centerline plane, I don't like either one of them where they go, or our centerline plane. Okay. So the part's going to sit on that centerline plane, and our secondary datum was A, which is this guy here. So what's going to happen first is you're going to have this collapsing cylinder hit here, but then this surface here is not going to fit nice and tight to this surface. So which one better describes the actual? It'd be number two here. So if I had to answer this question, I would describe part one, primary datum A, secondary datum B, and it's going to sit nice and flat when I go ahead and mate it up over here. And part number two, primary datum is B, secondary datum is A, and it's not going to sit flat in there. It's going to sit in the pilot hole, and the pilot is what's going to be able to constrain this more. Okay, let's take a look at this drawing and see what's wrong. If we take a look at the top portion here, we got a part. It's calling out this pattern of holes here. It's giving a position tolerance with a diametric zone of 8 thousandths to B and A. Let's take a look at what B and A is. Okay, okay, B doesn't look like it was qualified. It just gave a tolerance on the size of that pilot. But now we come to A, and normally you'd say, okay, yeah, A could be flat, but can it be flat to B? Probably not. You really can't have feature modifiers on form tolerances. So this is wrong here. What if you had this in there? What if you had perpendicularity, or you had position in there? Yeah, that would probably be okay. You could relate back to A, but not with this flatness, which is a form tolerance. These next questions I think we can get through fairly quickly. They're ones you've seen before. They come right out of your GeoTol Pro workbook. Let's see, click on both the symbol and name for each of the form tolerances. So what are the form tolerances? Yeah, we know we got flatness. Let's see what else we have. Cylindricity. Let's see what else then we have to click on. We have straightness. And we also have, let's see, any more? How about circularity around this? So we got 4 of them. So what's flatness look like in there? We got flatness. We said we had straightness. We said we had the cylindricity, and we also had circularity. Okay, let's submit. We're good. Okay, which of the form tolerances can have datum references in the feature control frame? Let's see now. It is pretty much like we had before on what's wrong with this drawing, but which form tolerances can have datum references in the feature control frame? So anyway, if we look at the datum references, can we be flat to something, or can we be circular to something? No. So the answer is going to be answer none. None of the form tolerances. Complete the sentence below by filling in the blanks on the drawing below. The maximum line element straightness of the pin before any geometric control is given. If we take a look at that, it's just going to be the size tolerance, or 0.5. Okay. Let's take a look at this next one. What rule in geometric tolerancing automatically controls the form of a feature within the specified limits of size? Limits of size, Taylor principles, rule number 1, the envelope principle, and it's all those. Okay, describe what is wrong on the drawing below. Let's see what's good to. Looks like a feature modifier there. Let's take a look and see what we got. This is a surface control, so MMC or LMC modifier cannot be applied to this control. So I'd say it's a straightness line element. It's a surface control. I can't use MMC. Let's go ahead and go along here. And a part of all, what is the flatness on the top surface with only the profile applied? We got profile. They got within 4. Let's see, 20. Let's see. So you got +2, -2 here. I'd say 4. Hit submit. Okay, what is the maximum cylindricity on a radius on the part below before any geometric controls are applied? So before any controls are applied, you don't have this here. You got between 10, 1, and 10. It's just going to be 0.1. What are always required with orientation tolerances? Okay, with orientation tolerances, say like perpendicularity or angularity, what you really have to do is be related to something like a datum. So datums is what you're going to need. Good. That's good. Name the orientation tolerances. Okay, well, we had 3 of them. And the 3 could really be wrapped up under 1, which would be really under this angularity, but it's angularity, parallelism, and perpendicularity. But they all could fall under angularity. Okay. Let's go to the next one. On the part above, what is the maximum variation in parallelism with only the profile applied? Let's see. It says with only the profile applied. Okay, on this one it might be worth drawing out, because it says on the part above, what is the maximum variation in parallelism with only the profile? So if we take a look at this profile and actually drew the zone in, we'd have a profile zone. I don't like the way that came out. Let's you have a zone here and a zone here, and basically you're going to have 5 below the line, 5 above. So if we had to get a parallelism, what could happen then? We could have something up and down in that zone of 10 thousandths. So the answer is 10 thousandths. Let's go ahead and put our 10 thousandths in. Okay. let's see, on the part above, can the MMC modifier be applied to the feature tolerance? Why or why not? Let's say the MMC. Okay, on this one here, if we look at the feature tolerance up here, it says this feature, it has a profile, it's got a parallelism, it's to A is down here. So what we're looking at now is that these are not features of size, but they're surface control. And you cannot have modifiers on surface features. So that's what would go into that one there. Let's go to the next one. Okay, it's a surface control. Good. With both the profile and parallelism applied to part A, what is the maximum height of the top surface? I'm going to stop this. We got to draw on this one again. Okay, so let's take a look at this thing, and I'd like to go ahead and draw this back in. It was both profile and parallelism applied to the part above. Okay, what is the maximum height of the top surface? So if we first go ahead and we draw in, see if I get this thing to draw for me. Let's go ahead. So if we take a look at this profile, we get a zone of 10 there. We get 10 thousandths. And what does this parallelism? It means you could be parallel within that 10, but it actually can float in and out. So you can actually put another requirement in there that we could put another zone in there that can float in and out within that parallelism. So it just refines that zone that we have up here in profile. So if this is 10 and we're allowed 5 on each side of the feature, what that's going to do is going to say, okay, from this datum A, we're going to measure up. What that allows us to have is, okay, somehow I erased part of the video on this one, but we're going to go over it real quick on this calculation, how we got what is the maximum height for the top of the surface to datum A. And, you know, again, we took a look at this profile requirement. There was a 10 thousandths profile requirement. So we'll just draw that 10 thousandths profile requirement in. And what that told us, on this side of the surface, there was 5 thousandths. And on this side of the surface, there was 5 thousandths. This next requirement for parallelism further refines this profile so that we could have another zone in there of 2 thousandths that further refines it, but that zone could move up and down within that 10 thousandths. But it's not really going to affect the height of the overall height with this basic dimension. So we'll take those off, because where we're going to get that height is, we're going to say we got this surface from this datum A. So from this datum A, we go up 1 inch, and we pick up another 5 thousandths. Okay, and then, so normally I would probably just write in 5 thousandths, but really it's 1 plus the 5 thousandths, which is going to equal 1.005. Okay, let's take a look at this one. It's explain the difference between the parallelism requirements and the drawings above. This is actually a problem right out of the book. I think most people are going to be comfortable looking at this here. It's something we've done before, where we have a feature that's being described by a profile tolerance of 10 thousandths in relation to A. And then it's being further refined by a parallelism tolerance of 2 thousandths. So if we take a look at this again, we could put the profile tolerance in, and then you'd have 5 on each side of the feature, but then we'd also have a parallelism requirement that would further refine how that would be. So this parallelism could float within that 10,000s profile zone. So I think most people get that. But what happens when we come over to here? You know, what's going on? We got this new T within a circle. So what does that mean? And you know, it's because it's a problem right out of the book. What I can do is go take a look at. I think it was 1116 is the page you want to take a look at. But this tangent plane, if we take a look at it, instead of being a requirement of parallel with all the points, it's actually if we had a surface and the surface, you know, it had some bumps and irregularities out of it. Okay, so that surface goes out. What we do is we wind up putting a plane that would touch on the high points. And you can actually put a surface indicator on that plane then, and that would then be your measurement. Because you're not picking up the points all in between, what's going to happen is it's not going to give you the flatness of that surface. It's going to give you the tangent plane to the high points. So in this case, the tangent plane of the top surface parallel to the bottom surface within 2. The tangent plane does not control the flatness. Okay, here's another one that will make you think. On the part above, can a datum or feature modifier be applied to this feature control frame? Why or why not? So we're taking a look at that, and you say, well, here's the feature, and it's pointing to a surface. So we're going to have to answer this one no. It's a surface control, and only features of size have modifiers. This is not a feature of size. Okay, on this one, on the part above, should the 25-degree angle, this guy here, have a plus-minus tolerance applied, or should it be basic? Couple things. You have a 50-50 chance on getting it right. The other thing is we've already shown that it is basic dimension right here. But the reason why it's supposed to be basic is controlled by this feature control frame and not by a plus or minus dimension. So the answer is basic. On this one, I think we talked about this before, that the angularity can be used for parallelism and perpendicularity. So in essence, you could have used either one of them and they mean the same thing. So that so there's no difference. Either one of these symbols could have been used interchangeably. Okay, let's see what we got. Okay, on this question, can a feature of size be controlled with 0 geometric tolerance? If so, if a feature is specified with a 0 geometric tolerance, what is required? So again, it's a poorly worded question because it pretty much gives you the answer. The answer is yes. It can be controlled with 0 geometric tolerance, and we found out in the videos and in the book. It's a very powerful tool. So what do you need then if you're going to use a 0 geometric tolerance? You're going to have a modifier like MMC or LMC. Okay, on this one, this is another good example of using 0 tolerance at MMC. On the part above, when the diameter feature size measures 11.9, what is the diameter position tolerance allowed? Well, if we go back and look at maximum material condition 11.1, you get 0. 11.2, you get 0.1. 11.3, you get 0.2. You get all the way up to 11.9, you're going to get 0.8. So the answer is 0.8. Okay.